In this problem, we are considering the function y equals f of g of x. And in fact here we have two functions which we can call u equals g of x and y equals f of u. And this construction is called a composite function, where we are using the output of g of x as the input of f of u. We can illustrate this arrangement using set diagrams as follows. We have three sets, A, B, and C. The input of G is A, and the output of G is B. The input of F is B, and the output of F is C. So G maps from A to B, and F maps from B to C. And so we see that the output of G is the input of F. So G maps from A to B, F maps from B to C, and we have a new function which maps from A to C, and we call this f after g, which we show on the diagram as follows. Now, we want to calculate dy by dx for this function f after g, and it's not clear how we will do so. So we need some intuition, and we can gain that intuition by firstly thinking about how much the output of G varies when we change the input by 1 unit, and the same for F. And secondly, by considering that if the output of G varies by 2 units when we change its input by 1 unit, then so does the input of F. So for a change of 1 unit to the input of G, we get a change of 2 units to the input of f. And we can demonstrate the relationship between these two functions graphically. Here we see two functions. The function at the top is y equals 6 times the natural log of u. The function at the bottom is u, which equals 1/2 x squared plus 2. For the function at the bottom, when the input x equals 2, the output u equals 4. And when the input x equals 2, we can show that the gradient at that point, du by dx, equals 2. And we're going to use the output of this function u as the input to the function y. Now the output of the function u equals 4, and we can show that the value of the gradient of y, dy by du, when u equals 4, is 1.5. The gradient of these two functions is indicated by the appropriate tangent line shown on each graph. And it should be clear that the lower graph shows the function u equals g of x, the upper graph shows the function y equals f of u. Now, on the bottom graph, we see that if we let x increase by 1 unit, then u increases by 2 units. And that is due to the fact that the gradient of the graph at the point in question is 2. On the top graph, if we let u increase by 1 unit, then y increases by 1.5 units, which is due to the fact that its gradient at the appropriate point is 1.5. And if we now rearrange these graphs so that the output of G becomes the input of F, we see that when x increases by 1 unit, y increases by 3 units. And it is clear that there is a multiplying effect that is at work here. In fact, we see that to get the gradient of the composite function, we must multiply the gradients of the functions that make it up. And so we expect a result of this form. dy by dx equals the gradient of f, f dashed, times the gradient of g, g dashed, which in this case equals 1.5 times 2, which equals 3. And with that intuition, we can start to solve the problem. Find the derivative of y equals f of g of x from first principles. So we let c of x equal f of g of x, and then by definition we have that dy by dx equals the limit as h tends to 0 of c of x plus h minus c of x over h. and we have corresponding definitions for f dashed of x and g dashed of x. Now, since c of x equals f of g of x, then we must have that c of x plus h equals f of g of x plus h. And so when we make the following substitutions in the expression for dy by dx, we obtain the limit as h tends to 0 of f of g of x plus h minus f of g of x all over h. And now we recall that our intuition suggests that we need to produce the product of f dashed of x and g dashed of x. And to do so, we introduce the numerator of g dashed of x, g of x plus h minus g of x, like so. And since we have put that quantity over the denominator h, then here we have produced the expression in g dashed of x. However, since we have introduced g of x plus h minus g of x in the numerator, we are forced to introduce it in the denominator, like so, so that the numerator and the denominator divide away to 1. And this is sometimes called the multiply by 1 trick, where we multiply the numerator and denominator of a fraction by the same expression so that we change its appearance but not its value. Now we note that we have the limit of a product of two terms, and we turn the limit of the product into the product of limits, where we can now note that the expression in the blue box is in fact g dashed of x. And so we obtain the limit as h tends to 0 of some complex expression all times g dashed of x. Now recall that our goal is to produce the product of f dashed of x and g dashed of x, or at least something like that, and we have g dashed of x. It's clear that we now need to work on the expression inside the square brackets, and we have to work it into some kind of form that looks more like f dashed of x. And the first thing to do is to reduce the denominator to a single variable. And so to do that, we let g of x plus h minus g of x equal d, so that g of x plus h equals g of x plus d. And with those two changes, the expression inside the square brackets becomes the limit as h tends to 0 of f of g of x plus d minus f of g of x all over d. And now we note that we have a problem, since we have a limit expressed in terms of h, yet we no longer have an h in the expression. So we have to rewrite the limit in terms of d. And that means we have to figure out what d does as h tends to 0. So we note that as h tends to 0, x plus h tends to x, so that g of x plus h tends to g of x, and that means that d, which equals g of x plus h minus g of x, tends to 0. So we can simply replace h tends to 0 with d tends to 0 to obtain this expression, which is written purely in terms of d. And now the expression in the square brackets looks rather like f dashed, but we can improve on this by making the substitution u equals g of x to obtain the limit as d tends to 0 of f of u plus d minus f of u all over d. We now note that the expression inside the square brackets is identical to the expression for f dashed of x after we have made the substitutions x goes to u and h goes to d. And so we obtain f dashed of u times g dashed of x. And recalling that u equals g of x, this becomes f dashed of g of x times g dashed of x, which as expected is a product of f dashed and g dashed. And so finally we have that if y equals f of g of x, then dy by dx equals f dashed of g of x times g dashed of x. Now, while this result is correct, it is not written in the standard form that we usually see at this level of mathematics. We can rewrite it in the standard form, however, as follows. We know that u equals g of x, so that du by dx equals g dashed of x. And y equals f of g of x becomes f of u, so that dy by du equals f dashed of u. Now we take the expression that we have derived and we make the substitution u equals g of x to get f dashed of u times g dashed of x, and on making these substitutions, we obtain dy by dx equals dy by du times du by dx. So we have that if y equals f of g of x and we let u equal g of x, then dy by dx equals dy by du times du by dx.